Right, so hello everyone. So today I'll be talking about this work on variational phase estimation, variational fast forwarding, which I did during my internship at CQC almost 2 years ago now. So I think David will be pretty familiar with this, but it only got published a couple of months ago. So yeah, so I'm going to kind of just go straight into it. Talk a little bit about this variational phase estimation method, the variational fast forwarding approximation, and then show some results. It shouldn't be too long, so if you want to stop me at any point or ask anything, or just shout because I can't see you. So
sure.
Okay, so this variational phase estimation is basically a non-orthogonal configuration interaction method of real-time evolved states. So we take an initial wave function, which can obviously be the Hartree-Fock or some other simple state that you can prepare on a quantum computer, and then apply real-time evolution operators with different times tj to get a series of states. We express our true wave function as a linear combination, and we try to diagonalize the Hamiltonian. Obviously, these time-evolved states will be non-orthogonal, so we need to include the overlap matrix. And in some sense, the idea here is that you should be able to use relatively short expansions. So the diagonalization part is not challenging. That can be done on a classical computer. What you are interested in doing on a quantum computer is getting out the elements of the Hamiltonian matrix and the overlap matrix between these time-evolved states. So in terms of this number of states that we need, we can consider our initial wave function, express it in the eigenbasis of the Hamiltonian. So here, n are the eigenstates of the Hamiltonian. And we can expect that this wave function has a so-called support space, which is smaller than the overall space of 4CI solutions. This can be exact in some systems, but you can also take this as an approximation, right? Even if you have your Hartree-Fock wave function and that has some contribution from every eigenstate of the right symmetry, you can take, a lot of these will be very small. So you can consider this as an approximation as well. So if we then look at our time-evolved states, we see that the time evolution operator doesn't really change the support space of the system, so of the function we started with. So in principle, we need a number of trial states that is larger than the cardinality of this support space to recover the full eigenspectrum within the support space. And this is where things get challenging, because on the one hand, these states are not guaranteed to be linearly independent. So you can imagine that by applying this time evolution operator enough times, you start generating fully linearly dependent states. And as I said before, this support space is usually an approximation. So actually, the number of states that you need is not necessarily well defined. And this is where this concept of phase cancellation conditions comes in, which was introduced in the original variational phase estimation paper, which gives us a mathematical condition that the functions need to obey in order to recover the full eigenspectrum. Sorry?
No, that was nothing.
Okay. So we can find these phase cancellation conditions under these assumptions that we have not guaranteed linear independence and small contributions from outside Q by taking a projector operator onto the trial states. And obviously this is kind of a complicated operator because the states themselves are non-orthogonal, but we can describe it in its action on each state individually, and it is easily related to the overlap matrix. If we put in the time evolution expansion, and the eigenstate expansion of the states into this operator W, then we end up with this expression on the right, hopefully, here, where we have this sum over the phases of all the time-evolved states. And essentially, we can see that if we constrain that to be a delta function, then we get an operator, that this W operator, this projection operator, collapses onto the projection operator of the onto the support space in the eigenbasis of the Hamiltonian. So this is in principle.
I'm not seeing where your non-orthogonality disappears to, but maybe because your phi's are not all necessarily orthogonal to each other. So your W projector isn't necessarily
exactly.
Idempotent, but your W projector on the right, when you go into the orthogonal basis of N and M, you don't have any S's in there, and that maybe that's exactly right, but it seems odd to me.
So bear in mind that this operator is diagonal, so it only has shared J indices, whereas this one has mixed N and M contributions, and I think that's where you're
right. Okay, yes, so that will give you okay, that makes sense. Okay.
Yeah, and then the whole point is if you take this coefficient to be 0 whenever the states are, or if you constrain this coefficient to be 0 whenever the states are not matched, then you end up with a true projector onto the support space. So this is just kind of a mathematical requirement on these states. It's not something that we will particularly impose in the rest of this talk, because we're only ever really interested in the ground state, and for that we don't need to span the full space. But it gives you a minimum number of states, so sort of the minimum NT for which you can satisfy this condition, at least approximately, gives you kind of the minimum number of linearly independent states that you need in your system. And you can think of this phase condition as basically sort of distributing your states along the phase of your states along the unit circle, so that you span the whole thing. So the neat aspect of this algorithm is that, as I said before, what we're interested in is how we generate the matrices, not so much the diagonalization, which should be pretty trivial. And in the presence of an evenly spaced time grid, these matrices end up having quite nice properties. So if we define our operator U to just be e to the minus I delta t for this even spacing in the time grid, then each of our states forms basically a power expansion. So this becomes related to Krylov subspace diagonalizations, which is similar to, for example, the Lanczos algorithm. Except in the Lanczos algorithm, you use the Hamiltonian directly. And it also has the nice property that in this case, the overlap matrix between any two states is the same so long as they are separated by the same amount of time, which means that the overlap matrix only has one unique row. So it requires a linear amount of computation in the number of states to compute the entire overlap matrix. Now, obviously, this doesn't help very much when we still have to compute the whole Hamiltonian matrix, but we can instead define this matrix of the U operator, which is related to the overlap matrix as shown here. So essentially, we can get the matrix of U by a transformation of the overlap matrix that is essentially free, and solve the eigenvalue equation for the matrix U, which obviously has the same eigenvectors as the Hamiltonian and eigenvalues that are related to the energies of the Hamiltonian by an expression that, well, by a linear expression, except for this phase factor, which can be problematic, but most often is not. So that means essentially we can get all these matrices in a linear, with a linear requirement for computation, and then the diagonalization is trivial. So all this work was previously presented in this paper given here, and what we worked on was how would you implement this in a quantum circuit. And the circuit we use here is of the form given here. This is a generalization of the Hadamard test, where essentially we create an entangled state in an ancilla qubit and use it to apply both of the time evolution operators that we need controlled differently, such that we get the state that we want. So if we look at this into a bit more detail, we have the time evolution operator, which we need to approximate by a Trotter expansion. And at the end of this circuit, we have a wave function of the form given here, which, ignore this zero index here, as a linear combination of states k and j, such that when we measure the ancilla qubit in the, there's an extra Hamiltonian in one of those. So if we only measure z on the ancilla qubit, we get the overlap of the two states. And if we measure z on the ancilla qubit, having applied the Hamiltonian to the system, we obtain the real part of the Hamiltonian. Obviously, here we're working with real Hamiltonians, so that's all we need, but we could get the imaginary contributions as well. So all of this looks very nice and simple and wonderful, except that when you look at the actual quantum resources that you need for systems that are not particularly large, you see that because of the Trotterized time evolution, the cost scales absolutely horribly with system size. So it very quickly becomes impossible to carry out these calculations. It's also worth bearing in mind that these are CNOT gates and just gates in general per Trotter time step. And obviously, the larger the system is, the larger the support space with your Hartree-Fock wave function, the more states you want to include. So you also need to do this Trotter evolution multiple times, more times the system size increases. So there's an extra factor that's not accounted for here. Which is why we looked at this variational fast forwarding approximation, which essentially gives a constant width approximation to the time evolution operator of the form given here. So we have essentially a similarity transform of this operator D, which is a diagonal operator. And this has a nice property that as you raise u to various powers, you only need to raise the diagonal operator to that power, and the w operators stay the same. In terms of how to express this, the diagonal part is usually expressed as products of rotation, z rotation gates. You have a choice on how many layers of rotation gates you add, and this product over J essentially is the number of qubits that are involved in the rotation gate. So we have 1 qubit rotations, 2 qubit rotations, and so on, and you can truncate this expression at some point, or you can, in principle, entangle your entire qubit register. And this has the property that raising it to a power really means replacing the coefficients with n times the coefficients. So it's very easy to compute. W is an arbitrary unitary matrix. It needs to be expressive enough for what you need. In principle, normally layered ansatz are popular. Here in this particular work, we used a symmetry preserving ansatz, which preserves spin and can preserve point group symmetry if you want to, which basically ends up with a circuit that looks a little bit like this. So we have the W matrix here formed of these layered A gates. And again, we have a choice on how many layers to include in the W ansatz. The diagonal part with these multi-qubit rotation gates, and the inverse of the W matrix.
Can I ask a question about your W's and D's? So if you did this exactly, it would be as hard as diagonalizing a Hamiltonian.
Yes.
So there's some magic going on here to make this good.
Yes. So I'm going to get to that eventually. But the first thing I would say is, so here in this case, we used mostly 1 and 2 layer Z ansatzes and also 1 or 2 layer W ansatzes, and you can get a decently performing approximation which uses about a comparable number of gates in the hydrogen case, but significantly fewer in the H2 case. Significantly fewer as you go up in system size, and most importantly, the width, the depth of your circuit is constant. So it doesn't matter how many Trotter steps you need to do, you never need to use more than this number of gates. So it's very promising. Now, in terms of optimizing this ansatz, okay, in principle, you do this by optimizing a cost function, which essentially is the overlap between this V operator, which is our approximate time evolution operator, and the true time evolved state. And we want this to match the action of the true time evolved evolution operator in the support space. So in some sense, we only need to diagonalize the Hamiltonian for the number of states that we're interested in, which is one thing. But because of the no free lunch theorem, so essentially what you mentioned before, this means that we would need a number of overlaps here that is greater than the size of the support space. And that's not very useful, because obviously computing these things is just as expensive as computing the trotterized state. So that's not very useful for our purposes. It also is the case that this variational fast forwarding only works for particular classes of Hamiltonians, where essentially sort of the information doesn't increase as you do your time evolution. And at least as far as I'm aware, it's not clear that molecular Hamiltonians in general fall into this class of operators. So it might well be that the VFF approximation is bad no matter what you do. But that's kind of fine. So we decided here to stop at 2 states in our optimization. You can try a single state, but we found that actually including the second state makes a significant difference, whereas going further doesn't really. And what we get is a set of states that are a power series of this V operator, and this is once again a Krylov subspace expansion. So the eigenfunctions of the Hamiltonian, or the eigenvalues of the Hamiltonian diagonalized in this space will still be correct, regardless of how poor an approximation to the time evolution the VFF actually is. And that's quite important. Here, obviously, there is one other risk. You can get a bad approximation that also sort of increases the size of your support space, that takes you out of the original support space. And that is more concerning, because then you need more vectors to get your answer than you would if you successfully avoided exiting your space. We still have the nice property that regardless of whether V is an approximation of the time evolution or not, the overlap matrix has this diagonal structure where you only need to compute the first row to get all the information in the matrix. But the eigenvalues of V are not related to those of H in general, because it's not an exponential of the Hamiltonian anymore. And they're also, the elements of V are not necessarily related to the, or this can be just the fact that the true time evolution matrix elements are no longer related to the overlap of these.
So are the eigenvalues of V just the elements of D? Because that's the diagonal. Yeah. Okay.
Yeah. Yeah, they should be. Although, so you need to express D in the basis of
the, yeah.
So the eigenvalues of D in the constrained space that you're working in. So you need to you still need to project D down into however many states you're using. So that's obviously a problem because it means that we can't use our linear approximation necessarily with this VFF. So we've made a gain because we no longer have intractable trotterized circuits, but we've also lost something because we can no longer compute our matrices as efficiently. So what we're interested in looking at, so I'll give some examples of a variety of testing this method out on a few systems. Things that are important to mention, the VFF circuits are optimized with state vector simulations. So optimizing these using shot-based simulations is difficult because you need quite good, you need the optimization to be quite good. We've done shot-based simulations using 10,000 shots per measurement and a linear dependency threshold of 0.1. So this is the point where as we're introducing these new states, these time-evolved states in our space, we check that the eigenvalues of the overlap matrix are above 0.1 and only keep that subset of the space. And that is to avoid essentially introducing states that are pure noise in the calculation. And we've also done state vector simulations, which can use a much lower linear dependency threshold, because in principle, states should only be linear dependent if they actually have an eigenvalue of 0 in the overlap matrix. So as a first quick example, the H2 molecules, the 3G basis set. So here we only have two states in our totally symmetric Hilbert space, the sigma G squared and the sigma U squared. So in principle, we need to hit two linearly independent states, and then we go from the Hartree-Fock energy to the full CI energy. So what we can see here is on the left, we have a case with quite a large time step, an increasing number of trial states using both the trotter time evolution and the VFF diagonalizing both the Hamiltonian in the VFF case and the U matrix, which is not guaranteed to give us anything useful, but in this case it does. And we can see here that with only two states in general, we stay on the Hartree-Fock, so that means we don't get our second linearly independent state, and then by the time we get to four states, we've got our second state and we converge to more or less the full CI energy within experimental noise. And then obviously, because there is some noise here, some methods converge on the second state as well. On the right, we have a total of 10 trial states with two different time steps. Now we can see you can end up in this other situation where if your time step is too small, then you basically significantly delay getting new linearly independent states in the system, and it will take much longer to converge to your calculation. So there's a balance here between the size of the time step. Obviously, the larger time step you use, particularly with, well, actually in both cases with the trotter expansion, you have a larger trotter error. With the VFF method, you're more likely to have a poor VFF approximation, so you're likely to fail at least to get these U matrix calculations to converge. So there's obviously some optimization to be done here with the parameters. If we move on to a slightly larger system, so H6, we can now see that there's a sort of stepwise convergence. On the right, again, we have multiple steps or different numbers of steps, and we can see that there's a jump from 2 to 4 and another jump from 4 to 8 as you reach towards the full CI energy. And again, we find that diagonalizing the U matrix in VFF gives fairly satisfactory results, despite the fact that there's not necessarily a guarantee on this. If we look at the behavior of the number of linearly independent states, we have the state vector calculations in dashed lines. We have the energy in dashed lines and the number of states in solid lines. So we find that if for the state vector calculation in orange, you get basically one new linearly independent state for every step that you take, up to quite a large number of steps, and the energy decreases nicely as you do that. The circuit case obviously has this much more stepwise behavior in both the energy and the number of linearly independent states, and that's because of the increased threshold, but at the same time decreasing the threshold will give us more states, but not necessarily states that actually belong to the space that we're interested in. And the VFF method behaves very similarly. It actually introduces slightly more states than the true time evolution in this case, but you do see that there's also still biases in both these methods, one of them positive, one of them negative, because of the because essentially we've not reached the correct number of states to get the true energy yet.
Do you know why 4 and 8 in the circuit? So why does 4 steps get you one extra one, and then 8 steps get you one extra independent?
That's a good question. I assume it probably is because, in some sense, I think in this case the states are probably relatively real, and that's as many time steps as you need to take to get over the imposed threshold.
Okay.
If that makes sense.
Yeah. Okay. Yes, there's the threshold there, but yeah.
Yeah. So I assume it's so if you had a larger time step, you probably be faster. And yeah, I expect it's pretty constant with the added phase. How much you need to essentially rotate to get away from your vector by enough that it counts as a linearly independent state. So as a final thing, we also looked at the convergence of VFF methods and this idea of how good does the approximation have to be. And in this case, we're looking strictly at diagonalizing the Hamiltonian. Obviously, for some of these approximations, diagonalizing the V matrix is actually really bad. So for here, we have 3 different time steps. And in this case, the dotted lines are circuit calculations, and the whole lines are state vector calculations. So we find some things that are mildly counterintuitive. So the first panel is the overlap between the nth trial state with VFF calculation and the true time evolved state. These are all for the 2-site Hubbard model. So again, we're in a relatively small Hilbert space, total of 6 states. And we see here that the state vector behavior is, we see here that it's not necessarily the smallest time step that has the largest preserved overlap. But once you go to quite a very large time step, you see that the overlap actually decays very quickly. But nevertheless, that doesn't impact the energy that we see. So in general, we find that the energy convergence is almost completely independent from the quality of the overlap that we get, but very highly dependent on the number of states that we can involve in our calculation. So the calculations with a large time step, which quickly reached a total of 6 states in our Hilbert space, converge to the full CI energy, whereas the calculations that stop at these 3 states fail. There's also this slight upward tilt of the energy in the circuit-based calculations, and I think that's to do with noise and the way that affects the states that are sort of actually being included in your. So when you do the transformation to the linearly independent subset of the states, you end up introducing slightly oddly behaving errors.
So in the left panel, if you didn't have any trotter error, you should just get a sinusoidal curve. Is that right?
If you didn't have any trotter error,
and you just did an exact propagation, you should end up,
No, so this is the overlap between a VFF state at time t and the time evolved state at the same time t. So it should be, if you have a perfect VFF approximation, it should be a flat line. So it should look like the orange line at the top.
Okay, so the green one is weird. Yeah.
Yes, the green one is weird. The green one, so the sinusoidal curve, you expect to, so you get a sinusoidal curve if you compared the first state with all subsequent states. That would be a sinusoidal curve. I don't really know what it says that the green. So the orange line at the top is sort of perfect. The other lines are kind of what you expect, that as you go away from, as your accuracy decreases, your overlap decays. Why? Yes, the green ones are adventurous curves. But in some sense, the point here is that it's fine, because so at least so long as you're happy to diagonalize the Hamiltonian rather than actually trying to diagonalize this overlap matrix of these states, you should get you still get sensible energies, even if your VFF approximation is bad, which is good because getting a good VFF approximation would be very expensive and not actually worthwhile. Yeah, so essentially we have this VFF method that offers a viable alternative for hardware implementation of the variational phase estimation algorithm. Your diagonalization results are resilient to VFF errors, and often we see that the VFF approximations can be good enough to use the linear scaling algorithm. I think, yeah, that is it for me. So yeah, are there any questions? Yeah. Thank you.
For your H6 energies, is it a problem that they're better than FCI?
Better than FCI is, I wouldn't say they're better. They are more negative. Yes. So I think essentially that's because we're diagonalizing this. Because we're diagonalizing the U matrix or V matrix, and because this is no longer the exponential of the Hamiltonian, it's just a matrix. It's not constrained to be variational with respect to the Hamiltonian.
Okay.
That diagonalization. So that's why in order to be able to do this, your VFF approximation has to be quite good, because if it's bad, things can go. You don't even have a variationality guarantee if your approximation is bad.
How painful is that convergence of the VFF? Getting that V matrix good.
Actually, for most of these systems, it's not hard. It's surprisingly easy, but it's hard to tell if that's. It's difficult to tell how that would scale to larger systems, to more complicated Hamiltonians. So this 0.5 time step is quite large. There's no reason you couldn't, 0.1 is fine, and at 0.1 you can get as you can see here, you can get very good. I think I'm presenting a different graph than I thought I was presenting. Sorry about that. Yes, this is not circuit and because the VFF optimization is always done with state vectors. This is the effect of using the second VFFs, so optimizing with one state versus optimizing with two states. So yeah, when you optimize with one state, in general, you get more decay, which makes sense. So anyway.
Any questions?
My understanding is the linear approximation is not valid when you trotterize.
The linear approximation is not, yes, it wouldn't be exactly valid when you trotterize.
So does all of this just come down to make a mixture of states and then, it doesn't, I've always thought of this stuff, it doesn't really matter that it's time evolution. The only thing that's important is you create a bunch of basis states.
Yeah, so it's basically just one of many of these Krylov subspace diagonalization methods, and you can make up your states in all sorts of ways.
Yeah. That's kind of what you see with this. That your green curve there is basically saying, I don't know, but it looks like it's almost out of sync with its time evolution. So the phases are going from -1. It's like a weird quantum oscillation.
No. Essentially this is what you're saying. Yeah, that what you want is a good way of generating states that quickly span your space of interest.
Presumably with that green curve, it's still, I don't really know, but so yeah, it's still doing quite well. Yeah, it's still getting the energy quite quickly, even though it's a terrible approximation of time evolution.
Yeah, exactly. So the green curve, particularly the solid green curve, gets the energy. It's only slightly slower than this orange one, which is not really. But yeah.
Do you think all of this would be clearer if people moved away from the time evolution and just tried to think about it as a way of generating basis states? Because you do all sorts of different things. I always think they're a bit constrained by that time evolution.
Yeah, I think so. I think there's this. The nice feature of time evolution is that it doesn't. If you have this approximation that you're in a subset of the full Hilbert space, and you do exact time evolution, then that subset never changes. Whereas if you do other things, you can end up increasing the size of your space. So you both need to get basis sets quickly, and you might also need to get more of them to redo the whole eigenspectrum. So that's the nice feature of time evolution, that in some sense it gives you a way to, given a particular quality of initial wave function, it gives you sort of a minimal number of states that you need to recover the eigenspectrum there. But it's not necessarily the most efficient way to get those states. So if you can find a better way to get the states, but without escaping, then
there's another angle from the quantum hardware point of view, which is in quantum hardware, it's kind of natural to think of time evolutions to implement them as quantum circuits. So it feels kind of native when you do Hamiltonian. You could also do powers of Hamiltonian or other kinds of functions.
But I suppose the key is you don't necessarily have to put the true Hamiltonian in. You're just generating space.
Yeah, so maybe that's another way to think about it, that you kind of want this exponential form of some Hermitian operator, but that Hermitian operator might be something.
And because you're trotterizing anyway, you're not actually applying the correct imaginary time evolution to the Hamiltonian. So, I mean, it's. I suppose one shouldn't worry too much about the trotterization.
Well, yeah, I mean, if you're doing it exact time evolution, it makes a lot of sense because, as you say, what you're doing is a purification scheme. You've got a mixture of eigenstates and you want to resolve out one of them.
Yeah.
Look at the interference. Yeah, no, it's interesting.
Can you go bigger than this H6?
If someone has the memory and the qubits, then sure.
But I mean that this goes back to how do you pick the time step for all of that time evolution? Yeah. And originally they try and do that, don't they, with the relative energy gaps in the spectrum, because that tells you how the interferences come in. Yeah. But if you start thinking about, do you want that to be small so your tropical error is small, or do you want it to be large so that you actually start to space more fast? It's not. If you just go, do you know what? We're just going to make a bunch of basis states and rediagonalize. And doesn't matter so much.
Yeah, but I guess presumably in any, well, I don't know actually. You might be able to design some routine for finding states that isn't sort of in any way parameter dependent. So you just generate them. But in some sense, especially if you want to do these power schemes, then inevitably you kind of have your smallest matrix is a parameter because all of these are unitary matrices. Inevitably you're doing this sort of rotation. So your initial matrix is kind of how far you rotate by. So you have to play around with that.
You alluded to the fact that the VFF scheme might not actually be able to represent the molecular Hamiltonian. It probably doesn't need to represent the whole thing because you only care about the ground state. Will that, do the numbers of resources that you put into it, does that still scale sufficiently so that you can definitely represent the ground state? If that makes sense, because you don't really care about all these excited states that you need to represent in doing this.
So I think there's a sort of a fundamental problem to do, I think, with that. I think it's to do with how entanglement in your system evolves as you do time evolution. It's or the amount of information in your system, this sort of thing. So I don't know if you're in a case of a Hamiltonian for which you can't do VFF. Again, I think for the H2 Hamiltonian you can actually do it. I don't know for other molecular systems. It's for the Hubbard model, you can actually do it. At least,
because of the locality in that, I suspect.
So obviously chemical Hamiltonians are also local. I just don't know if they're local enough. So I don't know if you have a Hamiltonian that's not variationally fast forwardable, I don't know what constraints that puts on essentially this eigenstate generation, because the representing the ground state, I think, comes down to being able to generate enough linearly independent states that you can sort of purify it out. I don't really know how those things are connected.
But surely you do need to represent the excited states as well, because those are what you're projecting out. When you do the subspace diagonalization, you're removing excited states from the ground state. So you need to have a good representation of all the states that are in your support states, or at least the low energy ones.
But so I think you get the same sort of thing you get in these iterative diagonalization schemes, where your ground state is better represented than if you actually look at the eigenvalues that you get, I think.
But you're going to be more efficient removing because you're removing excited states, you're going to be more efficient at removing them if you've got. If
well represented.
The time evolution of them is correct. Because that's what you're actually doing. You're kind of there in the diagonal part.
But it's about the support space. You only need to represent the support space rather than the whole of space.
This is where these phase cancellation things come in if you want to apply them, because it means that even if you're not perfectly in a support space, you can still perfectly represent well, not perfect, but you can get an approximation of how to well represent a subset of your
Other question? Okay, thank you very much, Andrea.
Thank you.
Have you ordered your pizza?
No, sadly, no pizza for me. I'm just watching enviously.
Thanks a lot for the talk.
Yeah.
And thank everyone for coming. And next talk is next week.
Next week, yeah. Yeah, next week. And next talk is Chaplain Oxford.
Yeah. So Gregory Boyd he actually lives in Cambridge. So
Okay. Really?
Gregory Boyd.
What's he talking about? That's that question.
It will be talking about LCU actually. It's the student from QCT.
He represented a poster.
Yeah, that's it. So if you want to join online, Andrea, feel free.
I mean, I don't know, do you have this set up all the time, or do you just have it because...
So no, the camera is always set up, so you can join all the time.
Yep.
Yeah, that might be interesting. Is it also Thursday, same time?
Yeah.
Cool.
Important.